Okay, and the next speaker is Rajeev, who's going to tell us about matched pairs of Lie-algebras in hydrodynamics.
Yeah.
So please.
Thank you. Yeah, I apologize for changing the title the last minute. I made the talk shorter, and so I changed the title to suit the topic. Yeah, so let me begin by thanking Bal for all these years of support and teaching me many things. In fact, I think I met you first in math science more than 40 years ago. Oh, Bangalore. Yeah, that's right. Yeah, that's right. Yeah, I had some visa problems, and he was the one. So, happy birthday. I'll begin with that. So, I'll talk about an old problem in physics. In fact, I believe it is the oldest unsolved problem in physics, which is to understand the flow of classical fluids. So, this is classical in the sense that no quantum mechanics, no relativity. So, not only is h bar equal to 0 and c equal to infinity, even the speed of sound is infinite. I'll talk about very low speed flow. It is rather remarkable that this problem is still unsolved, and one manifestation of it is the phenomenon of turbulence, which is still unsolved. I'm not going to solve it today, but I'll talk about some mathematical ideas that may help towards understanding it in the future. So the overall mathematical framework is quite simple, and probably Euler had some inkling of it, but there's a whole family of physical systems which can be understood in terms of Euler equations. So Euler equations are differential equations in a Lie algebra. So given a Lie algebra and a metric on the Lie algebra, you have a differential equation. It's important that this is not an invariant metric. If it's an invariant metric, the whole thing is trivial. So I'll think about a metric in the vector space of the Lie algebra as a map, as a linear map, from the dual of the vector space to itself. So this is sort of like lowering an index. That seems like the most convenient way to think about a metric. So given a metric in the Lie algebra, it defines a Riemannian metric on the Lie group, which is left invariant, because the Lie algebra is the space of left invariant vector fields. And therefore, there are geodesics in the Lie group. And the differential equations for the geodesic on the manifold of the Lie group can be translated to algebraic equations for the tangent vector, more precisely the cotangent vector. And they are these equations. So the cotangent vector to the metric tensor is called omega, and the derivative of omega plus the nonlinear term that follows it is the co-adjoint action of g omega on omega. G omega is now an element of the Lie algebra, so it makes sense to ask how it acts on omega, and omega is an element of the dual of the Lie algebra, so that makes sense. So that is a nonlinear equation. Now, if there's an invariant metric on the Lie algebra, not all Lie algebras have invariant metrics, but if there is an invariant metric on the Lie algebra, then I can identify the algebra and its dual, and then the co-adjoint and the adjoint representations can be identified, and this equation can also be written in this way. So this is a little more elegant way to think about it. No. This is, it's not like torsion. It is just ordinary Riemannian geometry. It's Riemannian geometry without torsion that I'm talking about. Yeah. No, both are without torsion. Yeah, the entire thing is within Riemannian geometry. Yeah. So the first example of this, yeah. If G is one, meaning if it is the invariant metric, then this vanishes. This commutator vanishes. And in that case, the solutions to the equations are one parameter subgroups. In other words, the geodesics in the Lie group are just one parameter subgroups. So the interesting case is the one where G is not invariant, and the solutions are more complicated. So the classic example of this, the one that Euler originally thought about, is the rigid body that we all teach in classical mechanics. So if you have a rigid body, then this omega is the angular momentum. The G is the inverse of the moment of inertia tensor. And so G acting on omega gives you angular velocity. So what this equation is saying is that the derivative of angular momentum plus the cross product of angular velocity and angular momentum is equal to 0. And angular velocity and angular momentum are related by the multiplication by the moment of inertia. So these are the famous Euler equations. I didn't write them down, but you can, I'm sure you've seen it in every book on classical mechanics. And these equations, Euler studied it, but they were completely analyzed by Jacobi years later. He solved it in terms of Jacobi elliptic functions. And it's a beautiful piece of mathematics. In fact, that work of Jacobi is the origin of the theory of elliptic curves, which nowadays is a fundamental part of much of algebraic geometry and mathematics. Now, independent of this, there is another set of equations in physics, also called Euler equations. These are the equations of an ideal fluid, an ideal and incompressible fluid. There's the Euler equations of rigid body mechanics. There are the Euler equations of ideal fluids. The Euler equations for the ideal fluids, remarkably, is another example of exactly the same system. So these two equations of Euler from very different branches of physics are really two examples of the same fundamental idea. And he probably had some inkling of it, although at that time ideas like Lie groups and Bi-Algebras were not present. He must have seen that there is some connection between these two systems. So what is that? So here the equations of motion, so the fluid is incompressible, which really means that the fluid velocity is much smaller than the speed of sound. That's what incompressible means. So this condition here is the conservation of mass, that the divergence of the vector field is 0. And this here is the conservation of momentum. So the left-hand side is the derivative of velocity. I'm using units where density is equal to 1. So this is really the derivative of the momentum of a small fluid element. And that is set equal to the force on that fluid element, which is the negative of the pressure. Now, notice that there is no equation for pressure. That's because the pressure really is like a Lagrange multiplier that enforces the condition of incompressibility. So you don't really need a separate equation for pressure. There are 4 equations and 4 unknowns. So it is best to eliminate pressure from the problem, and you can do that by taking a curl. The curl of velocity is vorticity, this omega. And now using some standard identities of vector calculus, you can show that the nonlinear term here, after taking the curl, becomes the commutator of these two vector fields. The commutator is defined like this. The commutator vector fields in the usual sense of Lie derivatives. So the Euler equations of an ideal fluid can be written in this form, where I have the derivative of omega with respect to time plus the commutator of v and omega is equal to 0, and v and omega are related to each other by a linear differential operator, the curl. So this is exactly like Euler's equations for rigid body motion. Omega is analogous to angular momentum, v is analogous to angular velocity, and the differential operator curl is the analog of moment of inertia. So the entire story is very similar. In fact, this analogy is not a coincidence. A few years later, a few centuries later, Arnold in the 1960s showed that this also describes geodesics in the Lie group associated to the Lie algebra of incompressible vector fields. Incompressible means the divergence is 0. So if you have two vector fields whose divergence is 0, their commutator also has divergence 0. That's because the commutator in that case can be written as the curl of the cross product. So the divergence is 0. So this set of incompressible vector fields form a Lie algebra. The corresponding Lie group is the group of transformations that preserve the volume element. And the operation of taking the curl defines an inner product in the space of incompressible vector fields. So it defines a left invariant metric on the corresponding Lie group, and these equations describe the geodesics in that Lie group. So this is an observation of Arnold, and he used that to prove some results about fluid mechanics. So I've always been very impressed with this geometric interpretation of a very simple set of equations. These equations look extremely simple. In fact, I would say deceptively simple. Although the nonlinearity is just quadratic, we still don't understand these equations. For example, there is no theorem in mathematics yet that proves that these equations have solutions which are non-singular for all time. Although recently there has been some progress on it, and most likely there are singularities. It looks very likely that there are singularities. But I won't address that. That's considered one of the major unsolved problems in the theory of partial differential equations. We don't the entire phenomenon of turbulence, which is still not understood, should in principle be a consequence of this rather simple set of equations. So it is worth studying these equations in some depth. They are at least as important to physics as, let us say, Young's theory or quantum gravity or problems of that nature. Oh, sorry, I somehow skipped ahead for a few. I don't know how that happened. Oh, I see. I am going the wrong way. That explains it. Okay. Okay. So the inverse of the moment of inertia is the thing that appears in the equation. The inverse of curl is a well-known Green's function, which I'm sure we have all seen. It's called the Biot-Savart operator. It appears in magnetism. The same problem appears in magnetism. Given a current, you have a magnetic field. The differential equation of the curl of the current is the magnetic field, is the Biot-Savart equation, and the solution involves this integral formula. So the operator G, what I'm calling G, which defines the metric in the Lie algebra, is the Biot-Savart operator. And quite a lot is known about it over the years. This problem arises in many places. So whenever you have a complicated problem, it's useful to study its lower dimensional analog. We don't understand turbulence in 3 dimensions, so we can understand the 2-dimensional case. Unfortunately, in 2 dimensions, the phenomenon of turbulence really doesn't occur. Even so, the mathematical structure can be understood quite well. I would say the 2-dimensional theory is fairly well understood by now. And the pioneering work is actually by Jens Hoppe, this man here. He has a PhD from MIT in '83, and his thesis had to do with membrane theory. And a big part of membrane theory is understanding the group of area-preserving diffeomorphisms. It plays a role analogous to the Verasoro algebra. And the way he studied it was, this was with Goldstone, was to somehow quantize that Lie algebra, and I will come to that. And then later he realized that this also has important consequences for fluid mechanics. And there's a very nice paper from 1993 where Hoppe explains this. So the key point is that in 2 dimensions, an area form, remember volume form in 2 dimensions reduces to area form. Area preserving diffeomorphisms in 2 dimensions are the same thing as canonical transformations. In fact, an area form defines a symplectic form. And here is a fluid mechanics way to see it. This is elementary fluid mechanics. If the divergence of a vector field is 0, it can be written as the dual of a curl. And this is called, such a vector field has a scalar potential. This scalar potential is called the stream function in old-fashioned fluid mechanics books. Now, the commutator of 2 vector fields, which is again of 0 divergence, corresponds to some sort of a Lie product among functions, scalar functions. And if you look at it carefully, you will see that it is just a Poisson bracket. So the commutator of vector fields corresponds to Poisson bracket of the stream functions. This Poisson bracket says that the 2 coordinates x1 and x2 are canonically conjugate to each other. And then the Green's function of the, moreover, if you look at the vorticity, and you think about, the vorticity is a scalar in 2 dimensions, because the curl of a vector field in 2 dimensions is a scalar. So you get a scalar. So this scalar of vorticity is related to the stream function through the Laplace operator. So if you think of everything in terms of the scalar functions, the Green's function G that I'm talking about, the metric tensor in the Lie algebra, becomes simply the Green's function of the Laplace operator. It turns out that the correct boundary conditions are the Dirichlet boundary conditions. And the Euler equations become a set of differential integral equations for a scalar field omega, where this is the usual Poisson bracket, where x1 and x2 are canonically conjugate to each other. And this scalar function A is the Green's function of the Laplace operator acting on omega. So this is the way Euler equations look in 2 dimensions. And this has been very well studied. In fact, being a very old branch of mathematical physics, 2-dimensional fluid mechanics has been studied for centuries. For example, we can solve these by analyzing them in terms of a Fourier series. If you impose periodic boundary conditions in space, which is not very realistic, but it's a technical trick that is useful, then you can expand them in a Fourier series. The Fourier coefficients have to satisfy a reality condition. The Poisson bracket becomes essentially the cross product of the wave numbers. There's some typo here, but the cross product of the wave numbers. And in order to be able to solve Poisson's equation, the total vorticity must be 0. And then you can solve the Poisson equation, and the Euler equations become this system of equations. It's a system of differential equations for the Fourier coefficients. Now, I will illustrate in this 2-dimensional context essentially what Jens Hopper did, which is that for many purposes, for example, in developing a practical method for solving these equations numerically, it is useful to replace a system of partial differential equations by ordinary differential equations. So you would like to truncate the number of independent degrees of freedom to something finite. But this is a tricky thing to do, especially in areas like fluid mechanics, because if you take a Fourier series and you simply truncate it by cutting off the high frequency modes, that doesn't work, because whenever you have nonlinearities, the product of two things with low momentum will go to the high momentum. So we understand this in quantum field theory. We have similar problems. So this is a problem of finding a regularization that preserves the symmetries of the problem, a gauge invariant regularization. In fluid mechanics, this is called the closure problem. The closure problem is that if you put a cutoff in the wave number, the nonlinearities cause higher harmonics that violate it. There is no elegant solution for this problem in 3 dimensions, but in 2 dimensions there is a beautiful solution, and that's what Mr. Hepe was talking about. So what you do is you can impose a periodicity not only in position space, but also in momentum space. Now this does not make much sense in terms of Euclidean geometry, but it makes sense in the sense of non-commutative geometry. Non-commutative geometry allows you to impose periodic boundary conditions not only in space, but also in momentum space. So if you do that, in 2 dimensions, there's a very elegant way to do that. And what happens is that the structure constants that appear here in the Poisson bracket, which was just P1K2 minus P2K1 is replaced, is deformed to this expression. In the limit as lambda goes to infinity, this reduces to the previous formula. Otherwise, it's not. But the remarkable thing is that this deformation still satisfies the Jacobi identity. That is the tricky part, is to find a deformation that satisfies the Jacobi identity. So this is called the sine Lie algebra. It appears in many places. So what is this Lie algebra? It's a finite dimensional Lie algebra. The dimension is of the order of lambda squared. It's actually lambda squared minus 1. And it is this algebra. It is a version of the unitary Lie algebra with a non-compact version of the unitary Lie algebra. So this corresponds to that. And the Laplacian 2 can be thought of as a finite dimensional matrix. Yeah, in the limit as lambda goes to infinity, it becomes the Poisson algebra that I had before.
Lambda plus 1.
Yeah, so in some sense, what I'm saying is that the group of canonical transformations is the limit as lambda goes to infinity of these non-compact unitary groups. So in the limit, it becomes the Lie algebra of canonical transformations. Now, of course, there are many different finite sequences, all of which tend to that same infinite dimensional algebra. This is one of them. The one that is appropriate for fluid mechanics is the non-compact unitary group.
Limit of un, right?
That's right, yeah. So this is a non-compact version of un. Yeah.
Could we use un also?
So that depends on the precise context. In fluid mechanics, this is the proper way to think about it, yeah. That's right. So there's a very nice argument by Boris Kaysen, who is a student of Arnold, that shows that with this, it has to do with which reality conditions you impose on omega. Okay, The point is that there is the complex Lie algebra GLN. It has many real forms. Which real form you pick depends on the precise conditions you put on these coefficients f. So the huh? Oh, that's a technical trick. The point about lambda being odd is that then there can be a primitive unit of unity whose square root is also a primitive unit of unity. This is something you need in order to do this business. There's a similar thing when lambda is even, but it requires a little bit of a technical trick. So I use the particular regularization. Remember, these are regularizations. So this lambda is not supposed to have any intrinsic physical significance. You're supposed to let it go to infinity. So you pick one that is technically convenient. That's why. It has to do with roots of unity. I'll explain where the roots of unity come from in a minute. This has to do with the interpretation of this in terms of non-commutative geometry, which I won't go too much into, but that's where it comes from. So then this system of differential equations become finite dimensional. So instead of the structure constants are these functions A, and these are the modified versions of the Laplacian. And now these are fairly simple to solve. And this way you can see quite a lot of interesting phenomena about two-dimensional fluid mechanics. And this, by now it's a fairly well understood thing. By the way, this idea of Heppe has been sort of rediscovered by people in fluid mechanics about 10 years later. And they've got all kinds of prizes for it. But it is actually, I think, Heppe who did it first. It's a paper in Fissure of Letters, in fact, where essentially this idea is rediscovered. It's all part of the same idea, because that's also part of this non-commutative geometry. Yeah, that's right. I would like to generalize these ideas to 3 dimensions. That's really what I want to do. But before I do that, let me make a little bit of a digression make some technical comments about the 2-dimensional case. So there is a way to understand where this sign Lie algebra and so on come from. And you should think of it as a kind of quantization. Remember, I'm talking about classical physics with nothing quantum about it. But quantization can be thought of as a technical trick. Quantization in this context is regularization. It is a way of replacing the infinite dimensional Lie algebra by a finite dimensional algebra. So imagine that I could somehow take a compact phase space, which is the torus, and I could quantize that mechanical system. Then it is pretty clear that there is a fundamental minimum unit of length, which is something similar to this h bar. And there is, because the overall area of the phase space is finite, there are just a finite number of cells into which you can divide. And therefore, there are only a finite number of independent quantum states. Therefore, the quantum operators, the Hilbert space is finite dimensional, and the operators are just matrices. And so the quantization of such a system gives you matrices. And that's the way to understand what went on earlier. There's a more detailed way to do that. I found this in this paper of Kaysin, Lubashenko, and Rajeev. None of this is in the context of fluid mechanics, although Kaysin wrote a famous book on hydrodynamics with Arnold. It's the same Kaysin. So here, they describe how to do this. What you do is that you look at the canonical, the Lie algebra of canonical transformations, and you quantize it in the sense that you deform it by using not the usual notion of a derivative, but a deformed derivative. It is one of these Q derivatives, Q deformed derivatives. So this is the kind of things that many of you have worked on. And the point is that such a derivative satisfies a modified form of Leibniz rule, where instead of the derivative being satisfying the usual thing, this is sort of twisted by an automorphism of the algebra. And now you take any function on the phase space, I can turn it into a pseudo-differential operator of this kind. And then there's a very nice calculus for such pseudo-differential operators, which is the Q analog of the Gelfand-Dickey symbol calculus. And so using all this, you can give a precise justification for that sign algebra trick. So I just wanted to mention this. to place it more in the context of this conference. Okay. Now, what I really want to do is to generalize all this to 3 dimensions. And immediately you can see there's a problem. You can talk about 3 dimensions, you cannot have a symplectic form in 3 dimensions. So it cannot be that obvious. But here is sort of halfway there. So it's useful to study an intermediate problem before looking at the full 3-dimensional case. Let's consider incompressible vector fields in 3 dimensions. It has 2 independent degrees of freedom because you have 3 components and 1 condition. It has 2 independent degrees of freedom. Let's cut the degrees of freedom in half by requiring in addition that the vector field preserve a scalar field alpha. This alpha is somehow arbitrarily picked. It is like one of the coordinates. Okay? So it is a function without critical points, meaning that the gradient of alpha should be non-zero everywhere. So there is a subalgebra of the Lie algebra of incompressible vector fields, which also preserves alpha. This simply means that the derivative of alpha along U is equal to 0. It is clear by construction that this is a Lie algebra because it preserves the density, it preserves alpha. So I call it 2.5 dimensional because it's sort of halfway between 2 and 3 dimensional. Now, such a vector field, which preserves both the volume form and alpha, can be written as the cross product of the gradient of alpha and A. This may look like a Klebsch decomposition, but I'm holding this alpha fixed. Alpha is fixed. So every vector field of this kind is of this type. Now, if you take the commutator of 2 such vector fields, that corresponds to a Poisson bracket on these scalar fields. So that is reminiscent of what happens there. This Poisson structure is defined in terms of this alpha. It depends on alpha. But it is not a symplectic form. It is a Poisson structure. And it is only in the surfaces where alpha is a constant where that is a symplectic form. The surfaces where alpha is a constant are the symplectic leaves. So there is a Poisson bracket. So this is a 3-dimensional analog of the story that we already had in 2 dimensions. But this is not enough to do fluid mechanics. I think I talked about this. This is not enough to do fluid mechanics. There is no fluid mechanics in 2.5 dimensions. Because remember that in addition to the Lie algebra, we also have the curl operator, or the inverse of the curl operator. The curl operator is not closed in that subset of Lie. So you have a Lie algebra of vector fields that preserve alpha, but the curl of that no longer preserves alpha. So you cannot do fluid mechanics with it. And that's easy enough to do by a short calculation. So we cannot do it there. So we really have to study both components of the vector field in order to study fluid mechanics. So this is something that people have studied. It's an old subject, so these ideas go back. So already in the 19th century, Klebsch and contemporaries produced various parameterizations of incompressible vector fields in terms of pairs of scalar fields. None of which, they're all quite complicated. The Klebsch parameterization, for example, is highly nonlinear, and it doesn't quite fit the kind of ideas that I'm talking about. There's something called the toroidal poloidal decomposition, which you'll find in papers of Chandrasekhar. So there's a long literature of it. But I propose in an earlier paper that we do this simple decomposition. That is, we do exactly what I said a minute ago, but you do it twice. So there is one set of vector fields which preserve some scalar field alpha. There is another set of vector fields that preserve another scalar field beta. Alpha and beta are independent of each other in the sense that their gradients have non-zero cross product. So they point in different directions. So they're independent in that sense. Every vector field which is incompressible can be decomposed in this way. And A and B are the 2 independent scalars. Now I'm cheating a little bit because there are a finite number of degrees of freedom associated with non-trivial cohomology. If the space we are talking about is not simply connected, there are some harmonic things you can add. I'm ignoring that, except for that. So every vector field can be decomposed in this way. Now, each piece describes a subalgebra because the vector fields that preserve alpha form a subalgebra, the vector fields that preserve beta form a subalgebra. So the situation we have is that we have a Lie algebra of incompressible vector fields. It has 2 subalgebras A and B, and as a vector space, S is the direct sum of A and B. Any element of the big Lie algebra can be uniquely decomposed as a sum of something in A and something in B. But here's the most important thing. This does not mean that this S is a direct sum of A and B as a Lie algebra. It is not. As a Lie algebra, it is not the direct sum. It is not a semi-direct sum either. Because although A and B are separately subalgebras, neither one is a normal subalgebra. So this is very different. So for example, if you look at the Poincare group, Poincare Lie algebra, the Lorentz algebra is a subalgebra. Translations are a subalgebra. But translations are, in addition to being a subalgebra, translations are also an ideal, meaning that even a rotation acting on a translation gives you a translation. So such a structure does not exist here. So this S is not a direct sum. So it is mathematical literature. This is denoted by this bow tie symbol. B and A act on each other. Okay. This is called a matched pair of Lie algebras. So we can study, and there is some literature about this in the mathematics literature. Suppose I am given two Lie algebras, A and B. How can I combine them to get a bigger Lie algebra S? Without assuming that A and B, that either A or B is an ideal of S. What conditions do you need? The necessary and sufficient conditions are called the matching conditions. So suppose I know the commutation relations in A, commutation relations in B. Now, what is not determined in S are the mixed brackets of A to B. So the bracket of something in A with something in B can be uniquely decomposed as something in A plus something in B. Therefore, it determines a pair of quantities, B acting on A and B acted upon by A. And the question is, what are the conditions to be satisfied by this pair of operations? And it turns out that these are the four conditions that must be satisfied. They're called matching conditions. Yeah. That's exactly what it is. That's right, exactly. This is the Lie algebra version of the bi-cross product. Yeah.
So what happens to the coproduct to the Lie algebra?
Yeah, we don't need the coproduct here because I'm not talking about a Lie bi-algebra. This is just a Lie algebra. I'll come to the connection to Lie bi-algebras in a minute. Okay. Yeah, so this idea has been discovered and rediscovered repeatedly in algebra. And it really, I think, goes back to Zappa in the context of groups. So Zappa discovered exactly the analog of this idea with groups. So you have two groups, how do you combine them to get a bigger group? So this bi-cross product, this is called the Zappa product. It was rediscovered by Takeuchi in the context of C-star algebras. Takeuchi. It is all in that context, that's right, yeah. So then eventually it was taken over to half algebras. That's right. It turns out that the Lie algebra version is a lot simpler than all of that. So I'm describing it in the language of Lie algebras. That's right. So the Jacobi identity requires these conditions. These conditions are exactly what you need to satisfy the Jacobi identity. That's right. These four conditions are necessary and sufficient for the Jacobi identity to hold. Any Lie algebra defines a half algebra. Beyond that, you don't need the half algebra. This is why I think it is easiest to understand it in the context of Lie algebras. No. These are all rather trivial half algebra. These are co-commutative half algebras. Because any Lie algebra defines a co-commutative half algebra. So the most famous examples of matched pairs are Lie bi-algebras. So the most famous examples are when these A and B are of roughly equal size and they are dual to each other with respect to an inner product in S. In that case, it is a Lie bi-algebra. But that's not necessary. The idea of a matched pair of Lie algebras is more general than the idea of a Lie bi-algebra. So I'll give here an example, which I think is an elementary example, which is an example of a bi-cross product of Lie algebras, bi-cross sum, I should say, of Lie algebras. And it is this. Take the Lie algebra of m plus n by m plus n matrices, GL of m plus n. It has a subalgebra consisting of matrices of this type. So the A0 is an m by m block, A1 is an m by n block, while B consists of an n by n block and an n by m block. So you can see that the product of two matrices of this type is again of that type. Similarly for B. So separately, they are Lie algebras, Lie subalgebras. The intersection is trivial. Only 0 is of both types. So GL plus n is a direct sum as a vector space of matrix of this. Any matrix can be uniquely decomposed as something of this type and something of this type. And separately, they are subalgebras. So you can ask, this must therefore be an example of a matched pair, and a short calculation will tell you that the action of B on A is given by this formula, and the action of A on B is given by this formula, and that they satisfy those conditions. So notice here that there is no reason why A and B should be of the same size. The dimensions of A and B are not necessarily equal. For example, M may be very different from N. But the most famous examples of this structure are the cases where A and B are of the same dimension, or more precisely that they are dual to each other as vector spaces. In that case, these are Lie Bi-Algebras, and this is an example in that case of what is called a Manin triple. But my point is that you don't need that. This idea is very general. So I think this is a very useful thing, because how do you study complicated groups or Lie algebras? You break them up into smaller things. Usually when you break them up into smaller things, each piece, at least one of the two pieces is an ideal. So for example, in Wigner's theory of representations of the Poincare group, he starts by studying representations of translations, and then he looks at the action of rotations or Lorentz transformations or translations. So they're using the idea that the translations form an ideal. But this point of view here, because you don't require the two pieces to be ideals, they also apply to simple groups. So simple groups don't have ideals. How do you break up a simple thing? The whole idea of a group being simple is that you cannot break it up into smaller things. You cannot break it up as long as you insist that each piece is a normal subgroup or an ideal. But here you don't have that. So in fact, there is some very nice body of work on groups by Agore and collaborators. Oh, okay. Okay, so I used too much of my time. Okay, so now we can apply these ideas to three-dimensional fluid mechanics. Okay, so I've introduced the basic ideas. So what we have is that So what we have is that we can take a vector field that is incompressible, decompose it as a sum of two terms, one belonging to each subalgebra, and then you can verify that there is an action of one on the other. So we can translate the commutation relations of vector fields to some sort of Poisson-like brackets on A and B. In fact, among the bracket of two things like A and two things of type B indeed are Poisson brackets. So the question is, what is the bracket of something of type A with something of type B? And that involves one of these actions of B on A and A on B. These subscripts correspond to differentiations. B2 means differentiate with respect to the second coordinate. So I'm using a coordinate system in which alpha is the second coordinate and beta is the third coordinate, and the remaining coordinate is along the cross product. There's always such a unique coordinate system. And you can work out that this is the Lie algebra of incompressible vector fields written in terms of these scalar fields, written in this language. So you just need to add a boundary condition of some sort. Yeah. For example, yeah, you can use Fourier transforms. Yeah. If you have periodicity, you can impose Fourier transforms. But that's not always the most physically correct boundary condition. But you need some boundary condition. Yeah, in fact, there's a whole story about boundary conditions in fluid mechanics, which is much like the story of boundary conditions in quantum field theory. Yeah. There's a whole theory of that. Okay, again. Yeah, so the other ingredient is the curl. So you can work out the curl in this language as well. And the curl is a sort of a 2x2 matrix of differential operators. So it's a short calculation to work that out. The inverse of the curl you can work out also. And now we have all the ingredients to write Euler's equation in terms of the scalar potentials. So we can take the vorticity, we can decompose the vorticity into a part that is within the subalgebra A, within the subalgebra B. And if you write it out explicitly in terms of coordinates, it looks like that. The second and third components involve only differentiations along the first coordinate, and then this has to do with the remaining differentiations. And now the velocity, which is the inverse of the curl, you have to actually calculate out. And so the scalar potentials of velocity are related to the scalar potentials of vorticity through this integral operator. So this thing here is the Green's function of the Laplacian, and so on. So it's a fairly straightforward thing. And you combine all this, and you can indeed write Euler equations in this way. So the first part of what I described, that the equations of two-dimensional fluid mechanics can be written in terms of some Poisson-like brackets and curl, can also be done in 3 dimensions. And this is fairly straightforward. This is not, so the important thing here is that this does not assume anything special about the vector fields. This is just the most general case. Okay. Now, what would you like to do with this? So one thing I would like to do, which I haven't been able to complete yet, I think it's a fairly difficult problem, is how do you regularize this problem? This is the fundamental problem that I would like to accomplish. This is an old problem in fluid mechanics. It has been with us throughout the entire history of fluid mechanics for the last 250 years. It is called the closure problem. How do you truncate this infinite dimensional system of differential equations to something finite dimensional without doing violence to the underlying symmetry, which is the Lie algebra? How do you replace the Lie algebra by something else? The difficulty here is that these Lie algebras are in some sense rigid. There's no way to deform them without somehow destroying the commutation relations. The hope is that you can deform them if you don't insist on them being Lie algebras, but something in a more general category, for example, Hopf algebras. Although they cannot be deformed within, so in the two-dimensional case, we could deform the Lie algebra of canonical transformations and replace them by another Lie algebra, which is this Lie algebra of unit transformations. That may not be possible in higher dimensions. And that is the direction I would like to go with this. So this is the idea of quantization as regularization. So it turns out that quite a lot can be done. I didn't want to write out long, complicated formulas. These ideas about taking a function. So what happens is that if you have a function of 3 variables, as far as A is concerned, x1 and x3 are canonically conjugate. As far as B is concerned, x1 and x2 are canonically conjugate. Therefore, I can turn A into a zero differential operator and B into a zero differential operator. And now the tricky part is to translate those matching operations. How does A act on B and how does B act on A? The product of B times A has to be rewritten as the product of the type A times B. And there is a way to do that using this simple calculus. And they lead to very complicated formulas, which I didn't want to write down. And if one can work this out in principle, I believe that there is a solution to this closure problem within this context. And the way things become finite dimensional is that this deformation parameter Q, when it is a root of unity, things simplify to a finite dimensional case. And it is this Q being a root of unity is where this odd, it is an odd root of unity. It is a root of unity of odd order. That's a technical simplification because in that case, the square root of Q and the square of Q are also primitive roots. So let me stop here. I'm happy to answer questions.
So in the example of quantization that you briefly mentioned,
Yeah.
if you quantize the phase space,
Yeah.
then and for instance, if the phase space is the manifold is finite. Is finite in size, so to speak. Then you get cells, right?
Yeah.
And there is we know the meaning. We have a physical meaning for that finiteness because
Yes.
there's an underlying fundamental constant that emerges,
That's
which
right.
is H bar.
Yeah.
So, in the kind of examples that you've been looking at, is there a similar fundamental constant that might emerge
Yeah,
for?
so here, remember, quantization is just a technical tool.
Right, right.
Yeah.
But
So
then the fundamental
that
constant.
lambda that I mentioned is
Yeah.
essentially 1 over h bar.
Okay.
Okay. So lambda going to infinity is the limit when you remove, that's why I call it lambda, because it's a
Okay.
cutoff. When lambda goes to infinity, it's as though h bar goes to 0. In fact, in a rather precise sense, lambda is exactly essentially 1 over h bar. Q to the power lambda in this deformation business is equal to 1.
Okay.
So
I was wondering whether there were more interesting length
Sure.
scales that might emerge, which have.
So, of course, I have an ulterior motive in doing this. I think that simply by studying old-fashioned subjects like fluid mechanics and trying to solve problems there using these ideas, we will learn something about how to do it in a fundamental theory also. So perhaps one message that I can say is that this story gives you a natural way of trying to construct diffeomorphism groups in higher dimensions in terms of diffeomorphism groups in lower dimensions. So remember I said here that the diffeomorphism group of 3 dimensions can be decomposed into 2 pieces. Now each of these pieces is essentially 2-dimensional because it is a direct sum of 2-dimensional canonical transformations on each surface where alpha is constant. So the diffeomorphism group in 3 dimensions, although it is intrinsically 3-dimensional, is the bi-cross product of 2 pieces, each of which is essentially 2-dimensional. And this construction essentially carries over even to higher dimensions. So for example, and it doesn't even require the condition of incompressibility. If you look at the Lie algebra of all vector fields in 3 dimensions, it can be broken up into 3 pieces. Each one is essentially 2-dimensional, and so on. So I think that one lesson you can get from this is an approach to constructing things like theories of quantum gravity based on this idea of decomposing it into lower dimensions.
Yeah, can I ask one? So in Hoppe's approach,
Yeah.
when you regularize that you're replacing
Yeah.
the diffeomorphism group with a
Unitary group.
unitary group.
Yes.
But diffeomorphism groups are intrinsically very different because the Lie algebra, it doesn't exponentiate to the group. So
Yeah. So, by the way,
is there some way of
yeah.
understanding that you're recovering that in the limit?
So the idea is that the regularization has somehow tamed that problem, but that problem will reappear in the limit in some way. Yes. Maybe that's what you mean. That's right.
But will it reappear in the limit? Or are you really losing that?
Yeah, I think it will reappear. In fact, there's a lot of nice work by Kaysen. That's what he has been working on geodesics, on diffeomorphism groups. And there are a lot of these phenomena that are sort of intrinsically infinite dimensional, which of course will not happen once you impose the regularization. But at least some of them I can see how they reappear. Okay, and I would say that these are analogs in fluid mechanics of what we call anomalies in quantum field theory. They are this phenomenon you're describing is analogous to an anomaly in quantum field theory. Of course, once you have a regularization, you no longer have an anomaly, but we understand how they appear in the limit. So this is an example of that kind of phenomenon. They're related to things like index theory, by the way. This thing that you mentioned is related to the index of some differential operators. So it's very much like the theory of anomalies. I think that's an interesting thing to study. Basically apply our knowledge of quantum field theory to these kinds of issues.
I had a question. So in the previous case, when you had alpha, when you had the Poisson manifold, so could you not just worked with Poisson manifolds and then some deformation quantization?
Yeah, so you can do that, but you'll only get half the story. You'll only get that A part of the story. Okay, you will not get the other part. So my idea essentially is that although the 3-dimensional space being a Poisson manifold doesn't recover the whole set of vector fields, each piece is a Poisson manifold, and there is this way of putting them together.
I see.
So this trick of combining 2 Poisson type Lie algebras will reproduce the entire thing.
So maybe
that is the new
in
idea
this,
here.
with this new parameterization, you still
Yeah.
have a Poisson manifold structure? Or
Each piece is separately a Poisson.
and this Bi-Algebra you got is like,
But once you take the
Yeah.
by cross product, it is no longer a Poisson.
it's
type.
not a Poisson
No,
manifold.
it's not. That's very important that it's not. Yeah.
So we can't do deformation quantity.
No. Yeah, that's right. We can do that. By the way, what I'm doing is basically that for each piece.
Yeah.
Okay. So my idea is to take this concept of deformation quantization for each piece
Combine.
and then combine them. And the whole intricacy is in how you combine them. That's where the whole thing happens.
Can I ask a question? I am a bit puzzled about the fact that three-dimensional diffuse can be constructed from 2D.
Yeah.
Because there are, for example, uncountably many three-dimensional manifolds. That is not the case with 2 dimensions, which are all connected subs, like orientable 2 dimensions. They are all connected subs with tori. Okay?
I don't know the answer
So-
to what you're asking because all my considerations are local.
Are local, no?
Yeah.
That's what I wanted
That's
to know.
right, yeah. So I have not really seriously studied what happens at the level of the complete manifold. Everything I'm doing is within some. Remember, I was using specific local.
So you are
coordinate
using
systems.
the fact that
Everything is local.
locally R3.
That's
Locally they are different.
That's right. So everything I'm doing is local.
What happened to that work called man in triple that you were telling before?
That's a particular case of this. Okay, so I didn't mention this. So my point here is that this is a bi-cross product of Lie algebras is a more general idea than Lie bi-algebras. But if you have an invariant inner product with respect to which A and B are dual to each other, it reduces to a Manin triple. Okay. So a Manin triple is a particular case of a bi-cross product.
Oh, I see.
Okay. And that particular case happens to be what is relevant for fluid mechanics because in fact this fluid mechanics has an invariant inner product
You need isotropic.
which is called helicity.
Isotropic.
Yeah, that's right. But I wanted to de-emphasize that part because I believe that this concept of bi-cross product of Lie algebras is more general and more useful in other areas.
Let us thank Rajeev
you.
again because we should move to the next speaker.